Syzygy, episode 80, Mapping the Unseeable. And welcome back to another edition of the Syzygy podcast. Joining me from her office just across the other side of town, not across the other side of the world, Emily Brunsden. Hi, Emily. How you doing?
Hello. I'm doing very well, thank you.
Good. So today we're going to be talking about a huge story which has been all over the papers again recently, which is apparently Einstein was wrong. Or not? I don't know. I mean, every blummin' time, Emily, something comes up where it's a tweak on the data, and there's really interesting, don't get me wrong, fascinating results about the cosmos. But can we please, for the love of everything important to you, not call it Einstein being wrong every single time? Is Einstein wrong this time, Emily? Just can we get this out of the way?
In a short word, no.
No, right. Einstein's very rarely wrong, probably because at the very heart of that phrase, Einstein is wrong, is a fundamental problem with the way we understand how these sorts of things work. Bottom line is, a bunch of astronomers have had a look up into the sky and found some really, really interesting data about dark matter and where it is in the universe. And when we compare that to our models, we find some interesting results. And that then gets translated as Einstein was wrong again. So we'll be getting to that in a minute. Emily's going to take us all through it because she spent hours trawling through this story trying to figure out what on earth is going on. But before we get to that, Emily, there's a couple of things in the news that we should probably talk about. Number one, did you catch the lunar eclipse last week?
Well, no, I was in the wrong half of the world, personally.
You were in the wrong half of the world. But did you get a lot of social media and stuff coming through on your feed, particularly from friends down under, saying, "Oh my God, look at the amazing moon! It's awesome." I did.
Yeah, I definitely did. My parents even went out and observed it. They stayed up late, bless them, to go and have a look at the lunar eclipse.
It seemed like the entire southern hemisphere had clear nights and fabulous observing for a beautiful, beautiful red eclipsed moon. And those of us in the northern hemisphere, I mean, look, even if we'd been able to, it's been raining here for about 16 years as far as I can tell. So we wouldn't have seen it anyway. So that's the lunar eclipse last week, and if you got to see it, that's fantastic. But coming up, there is another kind of eclipse. What's coming up, Emily?
So we've got a solar eclipse coming up. Now, this is, for us here in the UK, it's a partial solar eclipse. So we only get to see, I guess, a chunk of the sun being darkened out by the shadow of the moon.
Right. Do you have a sense of how much? Like, is it a tiny sliver? Is it half? Is it most?
It's sort of around about a quarter, just over a quarter of the sun being covered.
Still should look cool. It won't give us the full darkening of the whole world in a sort of apocalyptic kind of way, but it'll still look cool. Don't look at the solar eclipse, kids. Use a special piece of equipment in order to do that. But when's that happening?
So that's on the 10th of June. So it's handily sort of mid-morning for us here in the UK. But yeah, so if you are unable to have a device to look at the sun directly with, do be safe and use a proper solar viewing thing. Things like welding masks just don't protect your eyes enough from the solar radiation. So if you've got something, that's great. If not, then have a crack at grabbing some of the online web feeds. There's lots of telescopes around the world that are going to be pointing at the sun.
Particularly if you're in a part of the UK which, as I mentioned, has been basically underwater for the last 16 years because it just keeps on raining. And if the clouds are coming over, then there's going to be someone who's getting a decent view of it who's whacking it up online. So go and have a look at that.
Absolutely.
And that's 2 days after the other piece of news, which is that Emily and I are going to be doing a show. It's not a live in-person show. We're part of the York Festival of Ideas. So if you go to yorkfestivalideas.com.org.net, just Google search for York Festival of Ideas. We're on there doing a live recording of this podcast as part of the festival, and that's going to be loads of fun. It's not quite the getting back in front of a crowd that we like to do when we can, but it feels like a step in the right direction. And that's coming up on the 8th of June. Have you got a time? Do you remember what time it is?
It's in the evening for the UK.
Yeah. Can't remember exactly what time. I want to say 7:30. I could be wrong. I'll check
I think
with
it's
it to
8
make sure
o'clock.
that...
8 o'clock. You've got to be there at 7:30.
I've got to be there at 7:30. Right, okay. The rest of you can turn up at 8. Just go and Google York Festival of Ideas and you can find us there. And because the beauty of it is, because it is online, everyone can go. There's no limits on the number of people who can sign up for this one. It's not like we're going to sell out of seats here. So come and join us for that one. That's going to be a lot of fun. Anyway, we should probably get on to what we're actually talking about today, which is that poor old Albert is being beaten about the head again because obviously he's not the genius that everyone thought he was, because clearly he's wrong. Emily, where are we going to start on this one? Why don't we start with what's been measured? Who's been doing what in the astronomy gig this week?
Exactly. Yeah, I'm going to tell you what the headline should be. And let's be fair, many reputable news outlets have picked up this story and run with how the data are actually presented and what the actual scientific achievements are, which are fantastic, by the way.
Yeah. And it's fantastic to see this kind of science like getting all over the headlines. I think that's really, really cool. This is not, cure for cancer or a new COVID vaccine. This is esoteric cosmology and astronomy, and it's getting a lot of attention, which is great. So don't get me wrong. I love that. I just wish they'd stop with the clickbaity headlines. Anyway,
exactly.
What's been done?
So the headline should be that we have managed to create the largest and most detailed map of dark matter in our universe.
Right. So we're not in the galaxy, in the universe. This is a very large scale study, and it's a big old map of where the dark matter is in the universe at large. And I've got so many questions, but I'm going to hold off. I'm going to hang on to them, and I'm going to let you continue on. Who's doing this? How?
Well, it turns out there's a load of people behind such an enormous piece of research. It shouldn't really surprise you.
Not one dude in their backyard.
No, definitely not. So this is some group called the Dark Energy Survey Collaboration. It's a group that's in itself is made up of 400 people, 25 institutions, over 7 countries. Wow. So this is a big deal. And that's just the direct kind of people involved. Of course, then you rope in other people who come in and help out in different aspects as well. So yeah, it's a big collaboration, and the reason why they got together was to say, hang on, we've got all these wonderful cosmological models. We're making amazing simulations on the biggest supercomputers in the world to do this great science. But how about we just go out there and observe and make a map of where all the dark energy is?
Well, that's a good idea.
Dark matter is. Let's not go down that dark energy road.
Leave that out. So that sounds like a good idea, right? You got all your models. We think we know what's going on, but hey, says 400 plus astronomers, why don't we go and measure this stuff and find out where it is, and then presumably do a direct comparison? You've got a model that says it should look like this, and you've got observations that say, well, it does look like this, and how well do they overlap? I'm guessing that's the point.
Absolutely.
Cool.
Then it sounds like that should be fairly straightforward.
Yeah. How'd that go?
Well, the only problem is that dark matter is actually something that you can't see.
Ah, right. It's in the name, isn't it? Dark matter. Yeah, that was one of my questions, right? If you're going to make a map of where all the dark matter is in the universe, seems to me you've got a fundamental problem just straight out of the gate, Emily, which is if you can't see it, how can you map it? Right? It just doesn't make any plausible sense. So clearly I'm missing something. What is it?
Yeah, absolutely. So the reason that we know that dark matter exists is because it has mass, and therefore it has gravitational influence on stuff around it, stuff that we can see.
Right.
So for many, many years, we've been able to measure the presence of dark matter because it causes galaxies, including our own Milky Way galaxy, to spin faster than they should. Right.
Right. I mean, that's where all of this started, right? The whole notion of there being a need for dark matter in the universe came from observations of the rotation of galaxies and saying, well, hang on, if you add up all the stuff we can see and figure out how the galaxy should be behaving, it doesn't. It's just, you can't explain it with the stuff that we can see, so there must be stuff that we can't see, hence dark matter. And so just because you can't see it doesn't mean you can't see its effect, and its effect through gravity. So that's what they're mapping.
Exactly, yeah. And another very classic way that we've measured dark matter in the past has been when you take enormous clusters of galaxies And these big clusters of galaxies have dark matter kind of lurking around in the spaces between the galaxies. And then if you take the light that's coming from objects, say, even more distant galaxies that are behind these clusters, then that light on its journey towards us gets bent by the matter, the dark matter that's in between all the other galaxies in these clusters, and we get all these weird optical effects. So galaxies appear to sort of smear out to form arcs and parts of rings and all this amazing sort of stuff that we call lensing, where the matter is just basically changing the path of the photons on their way to us.
So how are they... Like, I can understand how you could do that. I could understand how you could look at an individual galaxy and say, well, it's doing this, therefore it must have this amount of mass in total, but we can only see this much, so do a subtraction, and this is how much dark matter there is. And I can see how you could sort of look at a particular, area of the sky and say, oh, look, I can see some gravitational lensing type weird bending effects there, so there must be dark matter in the way. What are they doing to actually make this map? Like, how are they figuring out how much dark matter there is across the universe in different places?
So they're taking exactly that same principle of that the dark matter is causing light to bend. So that example that I gave you we call strong lensing. It's when you get really, really strong, big clumps of dark matter. They're called quite dramatic effects. But what we're doing for the Dark Energy Survey collaboration we're looking at what we call weak lensing, which is when it's the same effect, except it's just happening to every single galaxy that you observe in the night sky. So every single, you look up, you make a picture of a particular galaxy. If there's any dark matter in between us and that galaxy, it's going to cause a really slight distortion in the shape of that image of that galaxy.
Oh, right. So they're able to actually measure, like the sort of effects that you see for gravitational lensing are like really quite weird, and they're beautiful, but it's like, a bizarre, literally a lens sitting between us and the thing further off through the universe, and it sort of just bends and stretches it out across the field of view, and it looks amazing and really quite weird. But this is much more subtle, and you can look at what presumably any galaxy and figure out from very subtle effects like that how much dark matter there is between us and them. Is that the idea?
That's exactly the idea. But if you want to do it on sort of the kind of scale where you want to create a substantially sized map of where all the dark matter is in the galaxy, in the universe, then you've got to do this like times, well, in this case, it's times about 100 million. So they've got 100 million galaxies that they've managed to measure for this survey.
Seriously. And so they're looking at 100 million different galaxies, and they're figuring out how much dark matter there is between us and them for each of those. And so from that, putting together all of those bits of data to say, all right, well, this must be where the dark matter is across the universe. And you can sort of lay it all out and map it out that way. That's very clever.
It's such a phenomenal achievement, just going from this idea of let's just make a map and just creating the map in its own right. So this the map was done from observations on a telescope in Chile. It's called the Victor M. Blanco telescope. It's a 4-meter telescope, so a pretty moderately sized telescope, and Cerro Tololo Observatory.
So just the one telescope?
Just the one telescope, yeah.
100 million galaxies.
So the
it's
whole...
been busy.
Yeah, exactly. It's pretty much dedicated to this project. They've been working for 6 years, so between 2013 and 2019. And what this result that's just come out is the result of the first 3 years of that data set. And it's taken a huge amount of effort just to get to the point of being able to construct this map, because the numbers are huge. We're talking about something like 5,000 square degrees of sky, which is something like 1/8 of the entire night sky, and including both hemispheres, which you can't see from a single telescope.
Yeah, that's a bit difficult. You're only ever pointing in one particular direction, so that's difficult. And so even with the rotation of the Earth, there's only so much of the sky that you can see. And I remember seeing from one of the images attached to the story that you sent me through about this one, Emily, that you kind of got to look away from the plane of the Milky Way galaxy as well.
Exactly.
You can't look through our own galaxy because there's just too much stuff in the way. So you're limited to the part of the sky which hasn't got us in it.
Exactly. Yeah. So you can only sort of see parts, but that's still, 1/8 of the sky is huge. It's massive.
Yeah, I mean, space is big, right? So, that still
Well,
leaves you a lot of galaxies that you can choose from. And turns out, you count them up as, 100 million or so that you said they've done? Which
100
is a lot.
million. Yeah. So they took data over a total of 758 nights. This is a lot of observing time, right?
Yeah. And that's still a lot of galaxies a night. Like, they've been super busy.
And they've been working with one of the best astronomical cameras basically in the field, which is a 570 megapixel camera.
Wow. Jeez. That's just, I mean, there's some very cool tools out there being used for this stuff.
Exactly. So as an astronomer, I can appreciate just how much data processing there is just to get those images off the camera into some sort of sensible format, let alone do things like identify all your galaxies, and 100 million of them, measure all your galaxies, and then construct that back into some kind of two-dimensional map. I mean, it's totally extraordinary, the amount of work that goes into just that kind of process.
You said that you can look at these galaxies, and we're talking very subtle distortions from the dark matter between us and them, right? So, in my mind's eye, I have, your classic picture, your beautiful astronomical pictures of a lovely big pinwheel galaxy or something like that, and being able to see subtle, weird distortions and stuff. But I don't think that's what you're talking about. So what exactly is it that they are measuring with these galaxies, and what are the distortions that we're seeing? Is it in, I don't know, is it in the spectra that we're getting from the galaxies? Is it like, what are they seeing?
It's not in the spectra. It's from the images, the photometric images themselves. And I, from my understanding, it's mostly to do with the brightnesses and where you find the brightnesses. So if you expect a typical galaxy to be bright in the center and then to fade away, then if you get a sort of sharper brightening in one half of the galaxy or something like that, then that tells you.
Right. It's what I just talked myself out of, which is I can't imagine that they're looking at all of these images of these galaxies and going, that's galaxy shaped, except it's got a weird bulge over here. It shouldn't look like that. Therefore, like I'd imagine it couldn't possibly be that because you've got 100 million of them. So how could you? But apparently that is. They really are looking for effectively visual distortions.
Exactly. Yeah.
Wow.
And well, let's be honest here. No one person, no horrible sort of PhD supervisor sat their student down and said, right, here we have 100 million galaxies. I want you to get through these by
Start
the end
at
of the
number
week.
1.
Okay.
Get yourself some coffee. You're going to need it.
When you got big data, you have to use really clever tools.
Yeah,
so
that's not even a bunch of honours students. You need computers for this one, presumably.
Absolutely. And you need the sharpest computers. So this is all done using artificial intelligence,
right?
Using machine learning.
Yep. So this is computers who know, in a sense of artificial intelligence, they know what galaxies look like. And so, they know it when they see it, and they know when they see something's wrong. And so they're just sifting through at supercomputer speed, looking for, that one's weird, that one's weird, that one's weird in this way. And they're able to extract from that not just a list of weird galaxies, but numbers that say, this is how much dark matter there is. That's awesome.
It's really, really brilliant. So I think this project did release some data after the first year. So a few years ago, they released just year one data. And it's phenomenal to look at basically every process that they have from acquisition of that image down to producing the map. They've had to build sort of new algorithms, new processes, new statistics of ways of analyzing the data, even in just from the year one release to the year three release. It's just phenomenal the amount of work that goes into producing something like this.
God, it's just the scale of it is off the charts, isn't it? It really is quite amazing. And no wonder it takes such a big team to figure this stuff out. And this is, well, we've talked about this before. The thing that amazes me about modern science in general and modern astronomy in the specific case here is how many different skill sets are required to come up with a result like this. I mean, you've got everything from how do we build and use some of the best astronomical imaging devices, telescopes and cameras that we can get our hands on, through to I've got to build and program a supercomputer to sift through this sheer amount of data and teach it how to do that itself. Like so many different crazy skills involved in modern science. There's something for everybody. It's great.
It is really brilliant. And it's, and it pays off because they've managed to put this this map together. So this is, I guess, the preliminary results, or the first results coming from the year 3 point. There are 30 papers that are journal papers coming out for this particular point. I think 29 of them are already published. I didn't read all of them, I have to confess.
Come on,
I did
Emily.
not read all of them.
What are you doing with your time?
I read a few of them, but it is just enormous amounts of stuff. And then you think, not have you just created this map of where all the dark matter is, but because you're looking at galaxies which are at different distances from us, which we measure using the redshift parameter, or basically how fast they're moving away from us due to cosmic expansion. So you get another piece of information that you can fold into this mix, which is actually time.
Right.
So you can say things not only about how the dark matter distribution looks in our local part of the universe, therefore basically now, but you can say things about what the distribution looked like in the past because you're looking at further distances.
Right. Further and further away is further and further back in time.
Just blows your mind, doesn't it?
Yeah. Although then you start to think about, but how do you then figure out where all the dark matter is now? Do you need to know where all the dark matter is now if you can only see, you can only see a bit of where it is now, and the rest of it is not now, and some of it's quite a lot not now. Like it's really, really not now in a very big way. I can't wrap my head around that one, Emily. But then the universe is weird like that. Looking just up into the sky is effectively time travel. So we have this amazing amount of data. Huge number of people have worked really, really hard. And we have a map. So, what does it look like? What is the map?
Well, you've got a picture of it in front of you. Why don't you describe to me what you think it looks like?
All right, make me do the work.
You're much better at this than I am, Chris.
Well, I mean, what I'm looking at looks like purple clouds, right? This is a picture which is from, so I'm looking at the article in the BBC News, but I'm sure this same picture, because it's from the Dark Energy Collaboration, is all over the media around this story. And I'm looking at an image which it really does look like, I don't know, it looks like sort of diffuse clouds. There's a sort of some dark bits and some very bright sort of pinky purple bits, and the rest is sort of cloudy, diffuse out. There is structure here, but it looks fairly random. So there are concentrated bits of bright stuff, which I'm assuming that's where the dark matter is. And there are, although maybe not, maybe the dark bits are where the dark matter is.
No, you're quite right.
There's contrast and different things here. So when I look at this, I see what looks to me like a fairly random blobby universe of dark matter, which is why I haven't got my name on any of the papers. So tell me what I'm looking at here.
I think actually fairly random blobby universe of dark matter is not a bad description as far as they go.
That's it. I'm publishing that one.
So absolutely, yeah. The bright parts of this picture or this map are the densest concentrations of dark matter.
Right.
So the brighter the purpley colour going to yellow. Also, by the way, why are all dark matter maps purple? I
don't know. Someone made that choice, right?
Yeah, they always seem to be. Anyway.
I mean, don't get me wrong. I like it. It's a nice colour scheme, but, weird.
So someone decided that at some point. Anyway, so you have these bright bits, and then you've got these voids, which is where the black bits are, where there's just no dark matter. And although we sort of see this as kind of a cloudy sort of structure, if you were to put this into a three-dimensional image, then you would see it's much more like a web. And we call this the cosmic web, right?
Right.
And on this sort of scale, on this sort of map sort of scale, it's you've got these clusters of bright dark matter, and we call them halos because in the center of those sort of spherical or extended blobby sort of smudgy clusters is where you're going to find the ordinary matter. So that's where you find galaxies, and that's where you find, of course, in the galaxies, the stars and the planets and all that kind of
and
ordinary
us,
mass
people
stuff.
like us, right?
Yeah.
And is that because like the bright bits on these maps, the blobby bits, the high concentration of dark matter, it's because of that's where we find the ordinary matter, or is it that we find the dark matter where we where we like which one follows which?
I think we
Do
generally
we find the ordinary matter because we've got the dark matter, or do we have the dark matter because we've got the ordinary matter, or is it just a hand in hand? How does it work?
The way we generally understand the universe is that the dark matter formed the structure which then the ordinary matter sort of collapsed onto.
Right. Okay.
So they are intrinsically linked.
Right. So what we're seeing here then is, in a kind of very real sense, the structure of the large scale universe. Right.
Exactly.
This is where all the stuff is in the universe. In which case, when you look at that again, what I originally described as sort of being, a purpley map with some blobby bits and some dark voids, why that's really interesting. Why do we have these really concentrated bits, and then why do we have these great voids with nothing in them? And what's it like in there? It's got to be a really lonely part of the universe to be stuck in one of those.
Exactly.
So that's very. I mean, it's not completely random, is it? It's not just this wash of spread out purpley dark matter. There's real structure here, and it's strung out on this web, as you said, this cosmic web, which is very cool.
Yeah, and although we're seeing all this lovely sort of structure in these kind of images, what we do have to remember, though, is that actually overall, things like the clustering of the dark matter, it's actually reasonably smooth. I mean, it could be a lot more clumpy than this. It's on the biggest scales relatively smooth, relatively even. We get these little kind of patches of high density, but over the very largest scales, and it is actually remarkably smooth.
So we have a map. We have on a very large scale. It's reasonably smooth, but it has this structure. We can see the cosmic web, and that is fabulous. But can I now go to the question of, okay, so what? You've got to do something with this, and you've actually got to compare it to what we thought this would look like. So I'm guessing that this is fairly close to what we expected, but from all the stories in the news, there's obviously some discrepancy. So, Emily, can you tell me a little bit about the other side of this story, which is, what did we think this was going to look like?
Yeah, so we've done these kind of surveys on smaller scales before, and there have been kind of hints that the same kind of result that the dark energy survey collaboration managed to get through. The reason why they're called the dark energy survey, by the way, instead of the dark matter survey, is because these things are all intertwined. So when you understand the full composite structure of the universe, so when you have kind of 100% universe, then if we know that 70% of that universe is in the form of dark energy, 73 roughly, 23% maybe or so is in the form of dark matter, and the less than kind of 5%, 6% level is all the other stuff, most of which is hydrogen and helium anyway, not even kind of interesting things like stars and people. Like the reason why they call it the dark energy survey is you want to understand the history and the evolution of the universe. You've got to understand all of the components, which dark matter is clearly a really important contributor to. So it's all kind of part of the same thing.
So is this kind of a this is a stepping stone to what they actually really want to get at? Like, okay, all right, we have to understand the dark matter first. Can we get that out of the way, and then we'll get onto the dark energy? Is this sort of step one for them?
It's all part of the same thing. So what we're trying to do is trying to construct a model for the universe. And the model for the universe says we had Big Bang. That's got its own sort of models. But then you sort of play the universe forward and you see what happens. And what is the model that describes the physics of how that universe, or our universe, evolves from day one? And I guess the standard model, we talked about the standard model of particle physics when we talked about muons. Yeah. There's a standard cosmological model as well. And the standard cosmological model, which is called lambda CDM, and this is where the Einstein sort of bit comes in.
Right.
The lambda stands for dark energy. So now Einstein didn't think there was such a thing as dark energy. He just shoved this lambda parameter into his equations, hoping it would sort of solve some problems with general relativity and the structure of the universe. Turns out it did.
Yeah, I mean, he came up with the idea in order to get himself out of a bind. That actually, it turned out, no, that's not a bind, Einstein. That's real. That's a real thing of the universe. Like, the theory needs the thing that he stuck in there as a bit of a fudge in order for it to be basically consistent. If you take it out, it just doesn't allow for all of the possible solutions to the equations. And so he put it in thinking, well, I kind of need this in order to make that problem go away. He's like, no, Albert, you're putting it in there because that's how the universe actually works, is the way it turned out. So
Exactly.
even that, like the whole dark energy thing, is pure Einstein. Like, he's not wrong about that. He's actually really right and vindicated. He just didn't think it was true at the time. So,
Which is all very ironic that we're saying that he's wrong now, but
yeah,
we'll come back to that.
Exactly. We'll come back to that.
So the lambda CDM, the lambda stands for the dark energy parameter, and CDM stands for cold dark matter. So these are kind of the way you've built up your universe with some dark energy, some cold dark matter, and bits of other stuff. Right.
See, the thing I like about this, just parenthetically, is that the standard model of particle physics is all the stuff that we really do get. And then, as you pointed out in your long list of problems, we kind of just try to ignore for as long as possible all the things that is broken about the standard model of particle physics. Your standard model of cosmology, right up front, names the two things we don't understand: dark energy and dark matter. Like, that's our model, but we don't understand them.
But we can model them really well.
Yeah. And don't get us wrong, it's not like we don't know anything about it, we just don't know what it is. I love it.
Yeah, and we can model them very well, and they do explain the universe around us really, really well, from the fact that the universe is expanding, the structures that we see, the way that dark matter behaves, all these kind of tests that we throw at the lambda CDM. It's passing, right?
Sure,
so this is good. Now, if I'm going to share my screen with you, is this going to work?
Yes, I can see that.
Can you see a funny plot?
I can.
So this is now where all the models and the map start to compare.
Right.
And this plot is it's quite a dense plot. So we'll kind of break it down, but this is kind of the core of interest here.
For listeners at home, have a look at your device if you've got the kind of device that can show images while you're watching a podcast, right? We've got some chapter art on here which is showing this graph right now, this plot right now, so you can follow along at home.
Mm-hmm. And if you're out having a nice stroll in the Howardian Hills or something lovely like that, which is where I sometimes listen to podcasts.
That's quite specific, but there we go. Yes. Hello to everyone out there on the Howardian Hills.
Then what you might want to try and imagine in your mind is that we've got a plot where we're plotting on the y-axis. What we're actually plotting here is the clumpiness of the dark matter in the universe, the clumpiness of matter, really.
Okay, so clumpiness up and down. Yep.
Yep. And then on the x-axis, we're plotting the amount of matter that's in the universe.
Okay, clumpiness versus amount. Yep.
And actually, it doesn't really matter what those two things are. The point is that we've got different ways of measuring these things using different techniques, and we're trying to make sure these things are consistent, because if they're all consistent, our model is great and we're away laughing, right? The understanding the universe.
Yeah. Okay, so with any luck, the different ways that we can measure these specific parameters of the universe will all line up happily, and we'll go, yep, we're on the right track. So describe to me what I'm looking at in this plot then.
So our gold standard that we've got the measurements from and already are the green circles. So we've got some green circles, two green circles kind of in the middle. And this is where the Planck cosmic microwave background has said that these parameters are from our measurements.
Right. And this Planck, that's your satellite, that's your orbiting telescopy thing, isn't it?
Yep, Planck was a space telescope that was observing the cosmic microwave background, which we've talked about before, but is the afterglow of the Big Bang, basically.
Right.
So we get to see that. It's a kind of a snapshot in the history of the universe at around 350,000 years after the Big Bang.
Right. And you said that's the gold standard. So we're really, really happy with the Planck measurements there, the Planck CMB measurements. We're pretty sure that those are good.
Exactly.
Right.
Well, at least they were definitely good at 350,000 years after the Big Bang.
Right.
Clearly, we've fast-forwarded about 13 point something billion years since then, which you can maybe dispute a little bit about where we are now. But, I mean, that's...
Put a tack in that one and pin it to the walls. Yep.
Yeah. But, okay, so that's our measurement that we had about this lambda CDM model of the universe. These are the values that we get from Planck. And now the grey circles, which have a black line around them, they are the new measurements that we have from this map of the distribution of dark matter.
Okay, so that's the new stuff. That's this new map, and they're highlighted on this plot as the dark blob. And so when I'm looking at that, I'm thinking, well, they overlap somewhat, but it's not great.
Yeah, so the outer circle of the green lines, which are the Planck lines, sort of go through a good section of the new observation lines. The two inner circles kind of touch, which are kind of, the most certain measurements, but they don't quite totally overlap.
Sure. Okay.
Or at least they do in the mass. So on the sides of this plot, you see these kind of peaks, and you can see that, say, if you look at the very top of the plot, there's a green peak that overlaps with a black peak. That says that those two are the same. Fine,
yep.
they
both
happily
agree. Yeah.
Yeah. On the side plot, you see that the green peak and the black peak are a little bit separated.
Yeah. I mean, we're sort of looking at this plot, and we're seeing different blobs, different blobby shapes, and in 2 dimensions, they don't agree brilliantly, but they sort of overlap in one direction, not so much in the other direction. So, okay, so what does that mean then? What's that trying to tell us?
So it tells us that broadly the two agree, but there is, and this is where the headlines are coming from, there is some possibility that they may not quite agree perfectly.
Right. And where they're not agreeing is sort of in the clumpiness side of things, that the Planck data says, well, it should be this clumpy, and the new map data is saying, oh, it's not that clumpy, it's this kind of clumpy. And is that where this discrepancy in the headlines is coming up?
Exactly, yeah. So we're sort of saying that the new measurements are suggesting that maybe we're measuring things to be a bit more smooth and more spread out by maybe on the order of a couple of percent.
Okay. Now, a couple of percent doesn't sound like much, except you can hide an enormous amount of really important physics or science in, a fraction of a percent, let alone a couple of percent. So if this were true, then a couple of percent discrepancy could be a really, really big deal to our understanding of the physics of the universe, right? That could really, really make a huge difference if this turns out to be true.
Yeah, and we have ways of quantifying that even better, right? We have different statistical tests. I think we've mentioned before sigma tests.
Yeah.
We require, if, for example, when we measured the Higgs boson, we required there to be a 5 sigma sort of probability that what we were measuring was actually exactly what we thought it was.
Yeah, 5 standard deviations away from these things line up perfectly and agree. No, they're actually different. Well, how different are they? Are they 5 standard deviations away from the mean of where we would expect them to overlap? Because if they're not 5 standard deviations away, we're not going to take that as a real result. And 5 standard deviations, like that's getting up into the 1 in a million chance or less of that being just a random, haphazard coincidence that you got this result. It's, in other words, that's your gold standard of, that's a real finding. The Higgs boson is real. This doesn't look like a 5 sigma result to me.
It's not. It's sitting, depending on how you want to measure it, it's sitting maybe around the 2 sigma.
Yeah. See, and this is where my problem with the headlines comes in. That if you're going to start saying Albert was wrong, I think, personally, it's just me, it's opinion. What do I know? My opinion is, you want something better than a 2 sigma result? 2 sigma results happen all the time. It's just a random roll of the dice. I mean, it's, can you put much faith in a 2 sigma result in astronomy, Emily?
Well, exactly. And I think the paper is really very clear in saying that these models agree to within the statistical tests that we can possibly do. And indeed, the press release that comes from this team doesn't mention this discrepancy really at all, which sort of sent me around in a few sort of circles trying to figure out where all this information was coming from.
Yes. Hang on, who exactly is disagreeing with who here? Everyone seems to be in full agreement. Oh, right. I mean, if I look at some of the articles that I came across, there were a few sort of quotes and statements that they managed to get out of people, either involved with the project or not. A journalist will go and ring up their local friendly astronomer or cosmologist and say, hey, what do you think about this? And some of the quotes are along the lines of, well, I mean, if this turns out to be a real discrepancy, then it basically turns everything that we know about the universe on its head. So, hey, whoa. We've got a long way to go before we get to that stage. So there's nothing wrong with the statement. It's true. There's just a really big if sitting in the middle there, which, as far as I can tell from my reading and from your reading of this, like, there's nothing in this result that says we need to throw out what we know about Einsteinian physics in cosmology. It just doesn't.
No, but I do understand it can be a bit disappointing, maybe isn't the right word, but a bit frustrating perhaps even if you are working on this. And I mean, we need results to be consistent. If you measure the same thing in two different ways, then it needs to give you the same answer, right?
Yeah, ideally.
So I guess in its ways, it's when you do the biggest, baddest, most amazing dark matter map that you could possibly dream of doing, and it still comes up with it kind of agrees, but maybe not quite. That is a bit frustrating.
What do we have to do here? What do we got to do? We threw we did 100 million galaxies, people. What do you want from us? Blood? Like, we did our best. But doesn't this, like, it reminds me so much of the particle physics thing that we talked about only a few weeks ago, right? Where there was this huge media interest in new physics. And it's almost sort of justifying the huge amount of effort that physicists, both theoretical and experimental at the massive Large Hadron Collider type organizations, have been throwing at these problems of trying to understand the universe. Actually, the punchline, I suspect, is going to be, yeah, but if you do your calculations properly, and, you know, at the end of our podcast on this, we talked about the lattice simulations, the computer simulations of the particle physics, which showed that maybe the theoretical result actually did come somewhat more towards where the experimental result was, and the discrepancy kind of goes away at that point. In other words, there was something wrong with the way we were trying to calculate. It's really hard. That's what happens the majority of the time when you've got a discrepancy between theory and experiment. It's not new physics. It's not throwing out the old. It's adjusting the way we're comparing them and doing our calculations or our measurements, and things come back into line. So, yeah, I guess I understand what you're saying, that it must be very frustrating to be on either side of this. You're either wanting these two blobs on this diagram to completely overlap and, yep, fantastic, we know we're doing the right thing, or you want them to be so separate that that's a sign that you're in a job for the rest of your life explaining that discrepancy. And instead you've got this overlapping but not enough kind of result. Yeah, I could see how that'd be a bit annoying.
Exactly. And it's one of these things where there's not obviously a thing where, if we just need to build a bigger particle accelerator and we'll solve this. We just need to build a bigger telescope and we can make more measurements. I mean, that is already underway, obviously. We've got these are just the first 3 years of the survey. We've got another 3 years of data that have already been collected that need analysing. So that's going to be obviously a big job for these cosmologists over the next few years. And I guess the same thing is true of the theories, and indeed the Planck models as well. You know, everyone's done their utmost, and there's been so much effort put into characterizing the tiniest little details that might influence the way that these measurements are put together. And I guess you get to the end of your long list of things that might be causing slight irregularities or ways that you can improve your measurements. You get to the end of that list and you think, you know, what do we do now?
Go back to the beginning and start again? I don't know. I mean, ultimately, right, the universe is the final arbiter of this. You can only compare what you can see to what you can calculate. And that, to me, there's a lovely lesson here in humility with both the particle physics one and with this one, which is we are throwing everything we've got at this, and the universe is saying, well, yeah, it's a bit more subtle than that. Go back and try again. And, we are really, really clever hominids. There's no question that as far as the broader ape family goes, we're doing pretty well on the intellectual front, right? We're good, but this is a lovely little sign, and so was the muon thing, that you got to try a bit harder. Come on, we're not going to give up these universal secrets quite so easily.
And I think the other thing that's really come to light, but in both these studies as well, I haven't mentioned it for this one, but there's a lot of removal of human bias that's starting to come into these sort of big projects in science, and that's a very, very good thing.
Did these guys do the result reveal party?
They didn't quite do the result reveal party, as far as I can tell, but certainly they took measures to sort of take away some of the key elements of the data when they were working with it, such that they couldn't introduce any human bias into the way that they looked at the results and processed the results.
That's
so
really
there were multiple steps along the way to try and make sure that there was no bias included.
See, I think this is a really interesting trend in modern science. And I mean, I'm only just hearing of it. It's probably been around for years. But the notion of actively removing the human bias element by physically separating the people from, the potentially biasing results along the way. I just think that's so cool. I think there's a lot of philosophy of science research to be done on this one. And I'm guessing there's also probably going to be a couple of cases where people have to turn around and go, that thing that we did where we thought we were removing all the bias, turns out we weren't. And there's some really interesting lessons to be learned. I think it's great. I love it.
It's really good. We've come a long way since Millikan and the oil drop experiment.
Oh, yeah. Yeah. We've come a long way from people just making up their own minds about what is and isn't an appropriate bit of data. I'll keep that one. I'll throw that one out. No. You don't even get to see the actual data. You get to work on this chunk over here, and we'll tell you whether or not you've done something appropriate at the end. I love it. I think it's great. Well, so we've got ourselves into this position, Emily, where here towards the end of the podcast, we've audaciously critiqued this massive, massive bit of research and come to the conclusion that, I don't know that there's anything in this, frankly. So look, listener at home, if you're actually from this team of researchers and you're sitting there just getting absolutely furious as you're walking across the Hawaiian hills and listen to the podcast, and you want to, give us what for, then you can always get in touch. But we seem to be in this position, Emily, where it kind of feels like we need more data. This discrepancy is either going to be there or it's going to go away. So where does it go from here? What happens next in this research?
Well, we do need to be a bit careful. I mean, it's very easy to finish at the end of every research paper to say, but we need more data.
Yes.
That might secure your funding in the short term, but
it becomes a bit transparent after a while, though. So, yeah, you said that last time.
Indeed, yeah. So we need to think cleverly about this. I mean, clearly, as I mentioned, there's another 3 years of data to come. So now I don't think there's any more sky. I think it's mostly refinement and future for more observations. So might get a little bit more sky, but
right. But it's not going to be another 100 million galaxies.
No, not as far as I understand. So there's going to be some new ways of looking at that data, ways of trying to pull out any systematics that are causing this discrepancy, maybe from the observational side. But I do think there's also going to be some renewed effort to go back and look at Planck. We have another crack at that, try and remove some of the systematics that might still be present in those data as well. But in some ways I sort of think, well, maybe we just need some more tests. So on that plot there were actually some other colours on there.
Going back into the wonkiness of the plot again. Yeah.
So there are some more circles on that plot which do give us some more information. So we do have information from things like redshift surveys, from local observations of things like supernovae in the local part of our universe. And that's kind of agreeing with both at the moment. So there is opportunity.
It's not helping
there.
Much. Yeah.
Well, it's helpful that it's kind of close-ish, but it's not solving the problem. So maybe there's refinements and more studies to be done in that area. And I might be being really optimistic here, but maybe we just need to dream up a new measurement. I mean, maybe we need to figure out what this dark matter stuff is to begin with, and then maybe we can make some progress.
Like, I just love the idea that this is a huge story and it's a massive bit of research in order to map out the stuff that we still don't know what it is yet. I mean, I know that's really important, and that's a massive, big step along the way to understanding all of this stuff. I'm not putting it down. It just makes me laugh that modern science is at this stage of, well, we know it's out there and we can map it. We can have really big studies and arguments about what the map means and how it lines up against other maps, but we still don't know what it is yet. Maybe you're right. Maybe when we find out what it is, that'll help us to figure out this plot.
So I think basically, if you're out there cracking away at dark matter, hey, even if you're out there sort of trying to figure out dark energy, I mean, props to you. You're doing a fantastic job. But can you just kind of get a wriggle on? Because we'd really like to sort this out now, please.
Right, well, having summarily pulled apart one of the most important and major publications in astronomy and cosmology for the year, Emily, I don't know, I feel pretty good about myself right now. This has been a fun conversation. I've really enjoyed it. So thank you for bringing this one to my attention. Emily, if anyone is out there listening and they're thinking to themselves, no, Chris just didn't get that, I need to put him straight on a whole bunch of stuff. If they wanted to get in touch with us, how would they do that?
Well, you can at us. We are at SyzygyPod. So
Don't
at
me.
SYZYGYPOD.
That's right.
So if you're not an atter, which is, I guess, a Twitter thing, I've just decided that atting is a word. I'm going to go with that.
Oh, look, go with it.
Yeah.
I think run with it.
If you're not an atter, then if you're on Facebook and you throw in Syzygy Podcast into the search bar, then you'll find us as well. On the Instagrams, which I think is something to do with pictures. I'm getting more information every day.
That's so old school. It used to be something about pictures, and now it seems to be basically everything, as far as I can tell. But sure, let's say that. On the Instagrams, we are also the Syzygy Pod.
Yes.
Do we have a website?
It is syzygy.fm, and you can find all the amazing episodes that we have done. You can find all the nice things that Chris has written up about each of the episodes, including some nice links and some plots. If you really want to go and study the chart that we've been talking about today and see if you agree whether or not they two measures in the theory agree.
Weigh in. Why not? We have. Yeah, you can find all
have
that.
a stare at it.
It'll
either make you incredibly happy or incredibly frustrated. I take no responsibility for either.
Oh dear! And listen, if you want to support us on this show, this silly thing that we do every once in a while, then there's a bunch of different ways that you can do that. First of all, you can just tell everyone you know that there's this show with these two people who prattle on about astronomy and cosmology, and you really should listen to it. Spread the word, share the link. You can leave us a review, give us some stars and a couple of words on your podcast client of choice, and that helps us to rise up through the noise and helps other people out there in podcast land find where we are. And if you want to become a financial supporter of the show, then you can join our fabulous patrons over at patreon.com/syzygypod. And for $1 a pound a month or so, you can help the electrons flow through our website and help us to do the things we love to do when the world is open up and coronavirus free, like festivals and gatherings and live shows. Looking forward to doing a bunch of those again. There's one last thing I want to mention, which is our wonderful friend Chris Baker, who is the fabulous astrophotographer behind the website galaxyonglass.com. Chris has been a friend of the show for a while and a supporter of the show, and he has a newsletter that he sends out once a month or so with a bunch of news and links and interesting things from the world of astronomy and astrophotography. And he's asked us to be a part of that. He's putting in a little feature about the podcast and a little bit of a write-up of some of his favourite shows from our catalogue, as well as our latest show whenever we put one out. So if you want to get over there to galaxyonglass.com, this is not a sponsorship so much as just a sort of friend of the show plug. So thanks, Chris, for everything you do. Go and check out his stuff. Emily, you've seen some of his stuff in person. In fact, I think the physics department at York, has some of his stuff up on the walls, don't they?
It is glorious. Actually, I even have one at home.
Seriously?
Yeah, I do. Yeah.
I'm so jealous.
His art. Well, I say art. It's this beautiful. The way that the universe is beautiful, and he just captures it straight away as an image from a telescope, sticks it on a piece of glass, and it's not tampered with. It's not kind of made too obtusely not astronomical. It's just a glorious telescope picture of a particular night sky object. Some of my favourites are in the catalogue too, and it just makes me really happy seeing them.
It is gorgeous. I'm looking at the website now, and there's this scrolling set of images of just basically the raw images, but also the artwork. He's got, framed images, backlit images, so you've got light coming through and just really making them shine. Do yourself a favour, even if you don't intend to buy one of these things, just go and look at the website. It's gorgeous stuff. So, galaxyonglass.com, sign up for the newsletter, and you can see some more stuff about what we do as well. Otherwise, Emily, I guess I'll catch you in a week or so's time. I don't know. I'm going to be taking a little bit of a holiday next week, so maybe 2 weeks' time. I'm going to see if I could get my way down to Wales and try to get out of the rain clouds. Said no one ever in going to Wales.
I went to Wales once, and it was sunny and warm for 4 days. So there you go.
You got the 4 days then, because I don't know that ever happens. So we'll be back again in a couple of weeks' time for another edition of the Syzygy podcast. Until then, Emily, see you later.
See you later.
Bye, everybody.